Hello, everyone. Welcome to our webinar today at Statistical Solutions. My name is Justin D'Souza. I'm a quantitative specialist here at the company. During today's webinar, we are going to discuss verifying of statistical assumptions. Things like normality and homogeneity of variance and linearity. I'm going to go through the entire presentation first, and then we'll do a Q&A session at the end. If you have any questions, you can type them into the chat box. My colleague Sierra has put some hyperlinks in the chat box as well for scheduling free consultations, and you can check out our website for free dissertation resources and the past webinars we've done. If you have any questions, you can type them into the chat box or the Q&A box. And we'll send everyone a copy of the presentation and the webinar today. All right, I'll give a brief overview of the services that we provide at our company. Then we'll look at statistical assumptions in SPSS, and then we'll conclude with a summary and a Q&A. So you can see on this slide all the different parts of the dissertation that we assist with. Our company has literature review specialists, quantitative specialists, and qualitative specialists. So we can help with virtually any part of the dissertation. If you hit a roadblock, you can just let us know. So we can edit your dissertation. For most of the chapters, we edit the draft that you send us. For the results, it's something we can provide an APA write-up. If you just give us your data and you provide us with your research questions or your methodology chapter, we can provide an APA write-up for you of the findings. You can see all the different parts. We help with developing research questions and hypotheses, framing your purpose and problem statement, identifying a gap in the literature. If you're doing a mixed method study, that's also something we can assist with. If you're doing quantitative and qualitative, we can help develop data entry templates for you if you're not using something like SurveyMonkey or Qualtrics. And then we can even upload a survey for you onto SurveyMonkey. And we assist with, all the chapters in the proposal, the introduction, methodology, and the literature review, and the discussion chapter and results. And then we assist with PowerPoints for both proposal and final defenses. And we can help condense your dissertation into a journal publication or submission. If you have any questions, you can give us a call at 727-442-4290. Okay, so assumption checking. What is the purpose of assumption checking? It's really done to make sure that your data are appropriate to run parametric analyses. I should say inferential analyses. It doesn't have to be parametric. It could be non-parametric as well. So most statistical analyses have underlying assumptions that you should verify before running the primary test. So first we'll look at normality, which is one of the more prevalent assumptions that you should check, especially if you have continuous data. So normality is run for primarily parametric analyses. If you're doing things like t-tests or ANOVAs or regressions or Pearson correlations, that's when you want to check for normality. So normality is making sure that your data resembles a bell-shaped curve. There are many ways to check for normality. And for many assumptions, there are alternative ways to check for them. So it's really important that you check with your committee what method they prefer for you to use, because you can check for normality visually, but you can also use tests that will objectively tell you if normality is supported or not. So we have the objective tests. Use things like Shapiro-Wilk tests or Kolmogorov-Smirnov test. And usually statistics, significance is a good thing. If you find a p-value lower than 0.05, that is usually a good indication that you have a significant relationship or a significant difference between your groups. However, for these two tests, a significant result is actually not ideal. So you want to find a p-value greater than 0.05 on these tests. What these tests are doing is it compares your data to a perfect bell-shaped curve. And if you have a significant result, that means that your data deviates from a perfect bell-shaped curve. So ideally, we want a p-value greater than 0.05 on this test. We want non-significance. And we'll take a look at some data to go over this. There are also visual interpretations. You can use histograms or normal QQ plots or normal PP plots. These are more subjective. I don't really prefer looking at visual interpretations for anything, for assumption checking, because it comes down to whoever's reading the paper. Someone else may interpret a histogram to be following a bell-shaped curve, whereas someone else might say, no, this appears to be skewed to the left or to the right, and it's not normal. So I prefer using Shapiro-Wilk and Kolmogorov-Smirnov tests. If the assumption of normality is not supported, the common approach is to shift to non-parametric techniques, or you can consider transforming your data using transformations. I leave that for a last resort. I try not to transform data because it shifts the entire interpretation of your data. Like if you transform it using a logarithmic distribution or an exponential curve, that shifts the interpretation for all your data. So I try to avoid doing that. Okay, and if you do have a normal, or if normality is not supported, then you can also try removing outliers. And we'll look at that on the next slide. Okay, so removing outliers is pretty important for most studies. You don't want to have extreme high or extreme low cases in your data, as that can cause skewness to the data, which will in turn cause normality not to be supported. So this is a citation I use all the time. You can standardize your scores. And if the z-scores, those are called standardized values, if those z-scores exceed 3.29, or if they are lower than negative 3.29, then those are outliers, and you should potentially remove those cases. Sometimes you don't want to remove outliers because taking out individuals from a data set is not telling a realistic depiction of the data. Sometimes you want to keep everybody in to be as honest and truthful to the data as possible. So you have to determine, that's also another question for your committee. Do they want you to keep outliers in or remove them? And you can also use box plots to visually identify outliers. So let's take a look at the first two assumptions. If you've joined us before, you're probably familiar with this data set. It's a spreadsheet that has car model statistics. So you can see a different car models in each row. And this is SPSS, by the way. So you can see we have mileage for the cars, horsepower, is the car using manual or automatic transmission, what is the weight of the car, and so forth. So say that we are proposing to run t-tests, or we want to run correlations, Pearson correlations, and we're using horsepower and mileage. These are both continuous variables. So you would need to most likely check for normality on this. And there are many ways to do it, as I mentioned. So the most common approach I see is going into analyze, and then go to descriptive statistics, and then go to explore right here. And you put in your variables of interest into this right box right here, dependent variable list. So let's just say we're looking at mileage and horsepower. Then you want to click plots right here. And we will check mark this box, normality plots with tests. And we will also check mark this box right here for histogram. And then we'll go to statistics, just check out everything here. I don't usually check mark anything here, even though there is an outlier check. SPSS does it a little bit differently than is conventional. So we'll look at outliers a different way. And then you click OK. All right, and that is going to present the output up here. And here we have our tests for normality. Okay, so we have the Kolmogorov-Smirnov test column, and we have the Shapiro-Wilk test column. Now going back to the PowerPoint, statistical significance is when you have a p-value lower than 0.05. If the p-value is lower than 0.05, then the assumption of normality is usually not supported. So that is what we find with this output here, is that both the Kolmogorov-Smirnov test and the Shapiro-Wilk test for both mileage and horsepower are significant. These are the p-values are below 0.05. So that would indicate that we probably are not meeting the assumption of normality, in which case you should shift to a non-parametric technique. And I do see we have a question. I was going to save questions until the end, but this is a very good question from Priya. Can you explain the difference between parametric and non-parametric techniques? Parametric techniques usually involve running continuous data. So if you have something like this, mileage and horsepower, something that is strictly a numeric value, usually you're going to use parametric techniques, t-tests or ANOVAs or regressions, or Pearson correlations. And normality is an assumption for many parametric techniques. As we can see with this example, normality was not supported, so I would shift to a non-parametric technique. So almost every statistical analysis has a parametric version. So have parametric techniques, which are t-tests, ANOVAs, Pearson correlations. The non-parametric alternative to these, every analysis tends to have a non-parametric alternative. So for a t-test, instead you would run a Mann-Whitney U-test. For an ANOVA, you could use a Kruskal-Wallis test. And for a Pearson correlation, you could use a Spearman correlation. Okay, so there's usually a perfect backup that you can run if normality is not supported. Okay, and then you can see if you want to go with the visual interpretation, here's the histogram for mileage and here's the histogram for horsepower. And neither of these resemble a bell-shaped curve. So, this is kind of a double check that, hey, the data doesn't appear to follow a normal distribution. Sometimes you will see significance up here, but then the histograms will look really good and they do resemble a bell-shaped curve, or vice versa. You could have a skewed distribution like this in the histogram, and then the Kolmogorov-Smirnov test or Shapiro-Wilk will support normality. So that's where it gets a little tricky, and that's where you have to determine early on, am I going to use a test of significance, or am I going to use visual interpretations? And that's where you have to ask your committee what they prefer. The next thing was looking at outliers. And the way to do this is by standardizing your scores. For this, you go to Analyze, and then Descriptive Statistics, and then Descriptives. And let's put in the same variables just for consistency, mileage and horsepower. The important thing you want to check mark is right here. You want to check mark this box here, save standardized values as variables, and click OK. What this is going to do is you see the original two mileage and horsepower variables here. These are the z-scores for the same variables, the standardized variables. And according to the citation, take a look at it here. So they say that 3.29 is the cutoff, essentially. Okay, and you just sort these columns in ascending and descending order. So if I sort mileage in ascending, we can see the lowest z-score is negative 1.43. That is not larger than negative 3.29. So we don't have any low outliers. Then you sort it descending. The highest z-score we have is 3.19. So remember, we're comparing it to 3.29 and negative 3.29. 3.19 does not exceed 3.29, so we don't have any large outliers, but this is pretty close. It's probably something you want to take a look at. So the mileage, that was this Lotus Europa that has a mileage of 43. That's something to keep in mind that could be skewing the data set. But I personally would not remove that case because it's not at 3.29. Then we do the same thing with horsepower. Sort ascending, no low outliers, and then sort descending. We do have a horsepower here that's very high. Okay, so this 460 for the Maserati Bora, that is an outlier. So typically what I would do is I would create a new variable next to it and copy all the data from here and just leave a blank right there. We want to eliminate that outlier when we run any descriptive or inferential analyses. And I would just call this horsepower outlier removed, like that. And then you'll use this variable throughout. Okay, so we remove the outlier for horsepower. The next common assumption is called homogeneity of variance. This is usually done when you're running t-tests or ANOVAs. So that's something I indicated here. If you're doing a t-test or if you're doing an ANOVA, which are parametric techniques, you want to check for homogeneity of variance. For this assumption, first you need to have your research question. And a t-test or an ANOVA, that's looking for differences between groups. So hypothetically say that our research question is there a significant difference in mileage in a car based on what transmission type it uses? You know, if we're using mileage and if a car's manual or automatic, is there a difference? You could do a t-test in that example. So homogeneity of variance is built into the t-test analysis. So if we go to analyze and then compare means and go to independent sample t-test, we'll put in mileage right here. And we'll put in transmission type right here. You have to define what the numbers are. So it's just 1 and 2. Click continue. So 1 was automatic, 2 is manual. And then click OK. All right, so this is what a t-test looks like. And you'll see homogeneity of variance is checked right here. Levine's test for equality of variance. So depending on how this result comes out, you should interpret the appropriate row in the t-test. Now we can see that there are 2 rows, equal variance is assumed, equal variance is not assumed. Findings for Levine's test work very much like the Shapiro-Wilk and Komorov-Smirnov test that we looked at previously for normality. Significance is not ideal for this test. So if you have a p-value lower than 0.05, that's not ideal. The assumption is not supported. And that is the case here. We have Levine's test, the significance is 0.011, which is not supporting homogeneity of variance. So in that case, you need to interpret the bottom row here. So equal variances are not assumed because Levine's test was not supported. We need to go across this row for the t-test. And we would use this t-value, and we would use this p-value. Okay. And when you do an ANOVA, it's very similar. If you go to ANOVA and same thing, we'll do horsepower or mileage and transmission type. For Levine's test, you go to options and you check mark this box right here, homogeneity tests. There are many things you check mark for ANOVA. I usually check mark descriptives, effect size, things like that. And then click OK. And this is what the ANOVA presents. And we can see that mileage right here is our Levene's test for homogeneity of variance. And again, it was not supported. Okay, and then we have linearity. Linearity is used usually when you're running correlations or regressions. And this is done visually. So it's checking to visually see if you have a linear trend between your independent and your dependent variable. This is done with scatter plots. Okay, so you go for this one, say we're trying to see, is there an association between mileage of the car and the weight? As mileage increases, what happens to the weight? Or rather, as the weight increases of a car, what happens to the mileage? So we'll go to graphs right here, graphs and chart builder. Then you need to select a scatter plot. We'll go down here and we're going to click right here and drag up a scatter plot template. Then we'll put weight as the x-axis variable, and we'll put mileage as the y-axis like this, and click OK. And this is what we have. And we can quite clearly see that there is an inverse trend here. As weight of the car increases, the mileage tends to decrease, which intuitively makes sense. The heavier the car is, the lower the mileage. But you can also, if you double click the scatter plot here, you can add a summary trend line. So if you click elements and then select this option here, fit line at total, that is going to present a summary regression line that pretty much summarizes the relationship between those two variables. And we can very clearly see there is an inverse negative trend between weight and mileage. Okay, so again, that is usually used for if you're doing Pearson correlations or if you're doing a linear regression. Okay, and then the last common assumption is absence of multicollinearity. And this is used when you're running regression models. And the assumption is making sure that your predictor variables are not strongly associated with one another. If you're doing a multiple linear regression, that means you're putting in multiple predictors into a model, and you want to see how it impacts an outcome. And one of the assumptions is that the predictors or the independent variables are not strongly associated with one another. And this is checked with something called variance inflation factors. And you can run this in the regression model itself. Okay, so let's come up with an example here. Say that we're looking at just random variables. How does displacement, weight, and quarter mile time predict mileage? Something like that. Okay, so we'll go to analyze, regression, and linear regression right here. Then you put in your predictors into the independent box. So let's say we're looking at, we'll keep it consistent. Let's look at horsepower, weight of the car, and displacement. And we'll put mileage up here. Now, to check for absence of multicollinearity, you need to check mark this box right here, statistics, and then select this option right here, collinearity diagnostics. And then you click OK. All right, and based on, most references say that if the variance inflation factors exceed 10, that is problematic. You can see right here, these are the variance inflation factors. And none of these values are larger than 10, meaning that displacement is a little high, but it's not above 10. But that means that there's not a strong relationship between horsepower, weight, displacement, meaning that we don't need to consider taking out any factors. Ideally, you don't have a strong association between any of them. And if you do, you want to consider taking out a variable at a time and see if that improves the model collectively. Okay. All right, all right, that pretty much covers it. Those are the primary assumptions. There are other assumptions that are highly specific to an analysis. If you go into statistics layered website, right here, statistics layered, and you type the analysis that you're going to run, like a t-test, independent t-test. This will give a solid explanation of what assumptions you should check. A lot of them are definition based. They aren't things you statistically have to check. Like for an independent t-test, you need to have a continuous dependent variable. That's not something we verify statistically. It's just a definition of how your variable's coded. Assumption 2 is that you need to have an independent variable with 2 categorical groups. That's either, that's built into how you're running your analyses. Independence of observations means that you can't have, participants can't fall into multiple groups. They distinctly fall into one group. Outliers is something we looked at. So I tend to use z-scores for that, and I standardize the values. We have normality, which we showed there are multiple ways to do that. In statistics layer, they talk about the Shapiro-Wilk test, which is what we looked at today. And then homogeneity of variance with Levine's test. So this is a great website. Sometimes I think they go a little overboard. Some analyses might have 10 assumptions to check, but I don't think every single assumption they list is of utmost importance. I think normality, absence of outliers, homogeneity of variance, those are important ones. But check with your committee. Your committee is going to have a preference for what you need to report. Okay, so if we have any questions, you can type them into the chat box. And you can also give us a call if you have any questions about the services we provide, 727-442-4290. Or you can email us at info@statisticsolutions.com. Sierra just put the hyperlinks in the chat box again. If you joined a little bit late, you can see those links. They are also at the beginning of the chat box, so you can see the free dissertation resources and scheduling consultation. But do you have any questions about assumption checking? If you do, you can type them into the chat box. And we will be sending everyone a copy of the webinar and a copy of the PowerPoint. If you have any questions about analyses to run, assumption checking, all right, thanks for joining, Heidi. Hey, Priya, I hope I answered your question about parametric and non-parametric. If I didn't, just let me know and I can try and explain it again. Okay, excellent. Okay, I'll stay on for a couple more minutes if we have any last questions. All right, thanks for joining, everyone. Come join us for our future webinars and let us know if we can be of any assistance. Have a great evening. Take care.